Hello, welcome back. We have been looking at this idea of continuity. And what we're going to do right now is try to see how we can apply the idea of continuity to an example considering coastal upwelling or downwelling. So we're going to start by getting ourselves oriented to how wind is going to move water in the ocean. So let's start by thinking again at this simple general idea, the simple general example here. A strong southerly wind is blowing in the southern hemisphere. Draw the wind vector and the direction of the Ekman transport. All right, so if we have a southerly wind, we remember that winds are defined by where they are coming from. So that means that we have a wind going from the south to the north. All right, so if a wind blows along the ocean, we remember that the air molecules have friction with the water molecules and they pull the water along in the direction of the wind. However, because we are on a rotating Earth, Coriolis will deflect the water away, so it doesn't move in the exact direction of the wind. In the northern hemisphere, Coriolis will deflect that water to the right. But in the southern hemisphere, Coriolis will deflect that water to the left. And we saw that as we go down throughout the water column, each layer of water pulls on the layer below it and turns it, and it gets turned as well by Coriolis until the resultant transport due to Ekman transport is going to be 90 degrees to the direction of the wind. In the northern hemisphere, that would be to the right, but we're in the southern hemisphere. So that 90-degree Ekman transport will be to the left. So if I draw an arrow to the left here, that means that my Ekman transport in the southern hemisphere, if I have a southerly wind going from south to north, is going to go from east to west. All right, so now that we've thought through, gotten ourselves oriented, let's go ahead and read our example. Assume you have a wind blowing from south to north, like we have right here, in the southern hemisphere at 20.0 meters per second along the Peruvian coast. The resultant zonal water current increases from rest near the coast to 0.70 meters per second, 50 kilometers to the west. All right, so let's draw that out here. Okay, so we have our Peruvian coast over here. We have our wind blowing along the coast. I'll put it up here. Our wind blowing from south to north. And so we're saying that right here along the coast, where this will be our 0 meters, this will be our origin. And we know that positive is to the east, negative will be to the west. So positive will be this way, and our negative will be this way. All right, so right here at 0 meters per second, our wind, we'll have our wind be, we'll have our water current be our blue. All right, so our water current starts out at 0 meters per second right here so it starts out at 0 meters per second right along the coast, and then it starts to increase, so it gets bigger and bigger. And let's say, and right here, it gets to 0.70 meters per second. And that point is at, it's right here on our x-axis at negative 50 kilometers. Of course, it's negative because this is our origin, and we're going to the west in the negative x direction. All right, so assuming our usual convention that east is the positive direction, what is the value of du dx? All right, so we want to find du dx. So that's what we're trying to figure out. So what is du dx? Well, du dx is just, we can approximate that as the change in u over the change in x. And so we know that the change in u is going to be, I'll write this down here again. So now du dx is going to be our change in u, which will be our u final minus our u initial over our x final minus our x initial. All right, so our u final is, then since we're assuming that it's going to the west here, is going to be a negative value. So that'll be a negative 0.70 meters per second minus our u initial, which was starting from rest, so 0 meters per second, over our x final, which is also a negative value. It's a negative 50, and I'll go ahead and convert that into meters, 50,000 meters, minus our x initial, which will be 0 meters. Now, the first thing that we want to notice is that we have a negative minus 0 over another negative minus 0. So what we know is that in the top, we have a negative value. So this will be negative, it'll be less than 0 in the numerator. And in the denominator, we also have something that'll be less than 0. And so overall, we're going to have something that is greater than 0, or a positive value. All right, so go ahead, turn this off and turn off the video for a second and do the calculation yourself. All right, so we see when we do our calculation that du dx is going to be a positive 1.4 times 10 to the minus fifth. And those units, if we look up here, that's a meters per second over a meter. So that just means that our units will be per seconds. All right, so let's talk about the fact that this is positive right here. All right, so this positive right here, what does that tell me? All right, so we have du dx is positive. So what that means is that if we were to draw our imaginary box in the middle of the ocean, as our water is coming into our box, since it's positive, what we're saying is that, and since we're going in this direction, I'll keep it consistent. So we're starting out at rest and we're increasing as we get into our box. So if I look at how much water is coming into the box on this side versus how much water is leaving the box over this side, I see that less water is coming into the box than is going out of the box. So the fact that it's positive tells me that I have more water rushing out of the box. All right. All right. So good. So is it negative or positive? It's positive. What does that tell you about what is happening to the water in the zonal direction? The water in the zonal direction is rushing out of the box. All right, so let's go to the next piece here. Assuming that the meridional current is constant. So that tells us that the north-south current, the meridional current, is constant. So that means that dV dy equals 0. And using what you know about continuity, what is the value of the change in the vertical velocity with depth dw dz? All right, let's open a new window here. And we can see that in this case, what we want to find out, want to think about continuity. So we know that continuity tells us that there are no holes in the ocean. So if water is rushing out of our box in one area, water needs to be rushing into our box in another area, another direction. Another way to think about this is that continuity is like chewing gum. And so if we stretch the water parcel in one direction, it must get squished in another direction. All right, so continuity tells us that du dx plus dv dy plus dw dz equals 0. That means that the change in u in the x direction plus the change in v in the y direction plus the change in w in the z direction must equal 0. And that can only happen if the water that's rushing into the box in one area, or it's rushing out of the box in one direction, is going to be piling up in the box in another direction. So we need to make sure that we have conservation of volume in our box. All right, so we are told in this example that dv dy is 0. So I can go ahead and cancel that term out of my equation. And so now I'm trying to solve for dw dz. So I see that I can now take this and say that now, if I just subtract du dx from both sides of the equation, dw dz must equal negative du dx. All right, so if we go back to what we had here, we saw that du dx was equal to positive 1.4 times 10 to the minus 5th per seconds. So that means that dw dz must be equal to a negative 1.4 times 10 to the minus 5th per seconds. All right, so in this case, we now have a negative value for dw dz. All right, so it is now negative. So what does that, so dw dz we see is negative 1.4 times 10 to the minus 5th. Is it positive or negative? It's negative. What does that tell you about what is happening to the water in the vertical direction? All right, so again, we need to think about what's going on in our box. So again, we have our box, our imaginary box, and I'm in the middle of our ocean. And if dw dz is negative, that means that we must have water piling up in our box. So if it's negative, that means that the water that's coming in here, if it's negative, that's going to be getting smaller. dw with z is getting smaller all the way up. And we know that at the surface, the water's not coming out of the surface, it's going all the way up to 0. So coming into our box, there is more water coming into our box than is leaving our box. And the box is not at the surface, because at the surface that would be 0. All right, so there is, so dW dz is d is getting smaller as it's going through our box. W is getting smaller as it's going through our box. So more water is coming into our box than is leaving our box. So the fact that it's negative tells us that water is piling up in our box. So more water is coming into our box than is leaving our box. So the water is piling up in the box. All right, so let's see. So now we've answered those questions. Let's go down to the very last question here. Assume that z is 0 at the surface. So we're going to define our z as 0 at the surface, as we typically do. And it's decreasing with depth. And that the vertical velocity at the surface is 0 meters per second, a boundary condition that we would assume. So we know those things. Those are things we can know. So knowing that, and we know what dW dz is, we can figure out the vertical velocity at a certain depth. And so we're going to figure out what is the vertical velocity at negative 100 meters depth. All right, so we're starting with the fact that we know that dW dz, we know this already, we found it already, is equal to negative 1.4 times 10 to the minus 5th per seconds. And the first thing I want to do is to go ahead and do separation of variables, which you can just think of as multiplying both sides of the equation by dz. So on this side of the equation, I'll still have dw, and that will be equal to negative 1.4 times 10 to the minus 5th per seconds. And over here I have my dz. Now I need to think about my limits of integration. So I can integrate both sides to get my w. And I'm going to go ahead and put my integral, take my constant outside of my integral on this side. And we are integrating from the velocity at 100 meters depth up to our velocity at the surface. And our depth we're integrating from, it's going to be a negative 100 meters up to our 0 meters at the surface. All right, so on this side, I just get W, which will go from, I should leave that as a negative, my W at negative 100 meters up to my W at the surface. And that will be equal on this side to my constant, negative 1.4 times 10 to the minus 5th times just z. That's the integral of dz is going to be z. And that will be defined from negative 100 to 0. So on this side of the equation, I have w at the surface minus w at my negative 100 meters. And that will be equal on this side to my negative 1.4 times 10 to the minus 5th per seconds times 0 minus a negative 100 meters. All right, so what I end up with over here, because W at the surface, we said that's going to be 0, so that's gone. So I end up with, I'll bring this up here. So this becomes our, if I do this calculation out, I get that negative W at negative 100 meters is going to be equal to a negative 1.4 times 10 to the minus 4th meters per second. So multiplying through by -1, I see that my velocity down at -100 meters is going to be equal to a positive 1.4 times 10 to the -4th meters per second. So this is telling me that I have a positive velocity going upward with a magnitude of 1.4 times 10 to the -4th meters per second. And so what I have right here is just an example of upwelling. All right, so that's how we can use continuity to help us to understand coastal upwelling.